NENOMATICA, where mathematics meets YouTube excellence. In this example, we will form a new quadratic equation whose roots are the cubes of the roots of the given quadratic. The original equation is x squared minus 3x plus 2 equals 0. Our goal is to build an equation whose roots are x sub 1 cubed and x sub 2 cubed. Step 1. Solve the original quadratic. The polynomial x squared minus 3x plus 2 factors as left parentheses x minus 1 right parentheses left parentheses x minus 2 right parentheses equals 0. Therefore, the roots are x sub 1 equals 1 and x sub 2 equals 2. Step 2. Define the new roots to be the cubes of the originals. Let y sub 1 equal x sub 1 cubed and y sub 2 equal x sub 2 cubed. Substituting our values gives y sub 1 equals 1 and y sub 2 equals 8. Step 3. Use sum and product of roots. For a quadratic with variable y and roots y sub 1 and y sub 2, the standard form is y squared minus sy plus p equals 0, where s is y sub 1 plus y sub 2 and p is y sub 1 times y sub 2. Here s equals 1 plus 8 equals 9 and p equals 1 times 8 equals 8. Step 4. Substitute s and p into the template. Therefore, the required quadratic in y is y squared minus 9, y plus 8 equals 0. Step 5. Verify quickly. Plugging y equals 1, we get 1 minus 9 plus 8, which is 0. Plugging y equals 8, we get 64 minus 72 plus 8, which is 0. So the equation y squared minus 9, y plus 8 equals 0 indeed has roots 1 and 8. In this example, we will form a new quadratic equation whose roots are half of the roots of a given quadratic. Here is the example we will solve. We start with a key fact. For a quadratic ax squared plus bx plus c equals 0, with roots x sub 1 and x sub 2, the sum of the roots is negative b over a, and the product of the roots is c over a. Applying this to x squared minus 2x minus 3 equals 0, the sum x sub 1 plus x sub 2 equals 2, and the product x sub 1 times x sub 2 equals negative 3. Now, define the new roots y sub 1 and y sub 2 to be 1/2 of the original roots. That is, y sub 1 equals 1/2 x sub 1, and y sub 2 equals 1/2 x sub 2. Then their sum is 1/2 times x sub 1 plus x sub 2, which equals 1, and their product is 1/4 times x sub 1 x sub 2, which equals negative 3/4. A monic quadratic with roots y sub 1 and y sub 2 is y squared minus the sum times y plus the product equals 0. Substituting s equals 1 and p equals negative 3/4 gives y squared minus y minus 3/4 equals 0. To clear the fraction and write integer coefficients, multiply both sides by 4 to get 4y squared minus 4, y minus 3 equals 0. Let us verify this with a second method. If each new root is 1/2 of an old root, then x equals 2y. Substitute x equals 2y into the original equation. Therefore, the required quadratic equation whose roots are half of the original roots is 4y squared minus 4, y minus 3 equals 0. In this lesson, we form a new quadratic equation when each root is shifted by 2 units. We will follow 2 clean methods and verify they agree. First, the word example appears, followed by the problem statement in orange bold math. The given equation is x squared minus 2x minus 3 equals 0. We must create a new quadratic whose roots are 2 more than the original roots. To keep this interactive, watch for the challenge, tip, and celebration emojis as we go. Method 1. We will use the identities for the sum and product of roots. For ax squared plus bx plus c equals 0, the sum is negative b over a and the product is c over a. Here it equals 1, b equals negative 2, and c equals negative 3. So x1 plus x2 equals 2, and x1 times x2 equals negative 3. Define new roots y1 equals x1 plus 2, and y2 equals x2 plus 2. We compute their sum and product. The new sum is y1 plus y2 equals x1 plus x2 plus 4, which becomes 6. The new product is y1 times y2 equals x1 x2 plus 2 times x1 plus 2 times x2 plus 4. That simplifies to negative 3 plus 2 times the sum plus 4, which equals 5. Once we know the new sum capital S equals 6 and the new product capital P equals 5, the quadratic with these roots is y squared minus sy plus p equals 0. So the answer is y squared minus 6, y plus 5 equals 0. Method 2. Verify by substitution. If y equals x plus 2, then x equals y minus 2. Substitute into the given equation and simplify. Both methods agree. The quadratic whose roots are 2 more than the roots of x squared minus 2x minus 3 equals 0 is y squared minus 6, y plus 5 equals 0. In this lesson, we will form a new quadratic equation whose roots are the squares of the roots of a given quadratic. The given equation is x squared minus 2x minus 3 equals 0. We will use Vieta's formulas to avoid finding the original roots directly. By Vieta's formulas, for ax squared plus bx plus c equals 0, the sum of the roots is negative b over a, and the product is c over a. For our equation, a equals 1, b equals negative 2, c equals negative 3. So the sum s is 2, and the product p is negative 3. Let the new roots be y1 equals x1 squared, and y2 equals x2 squared. Their sum is x1 squared plus x2 squared, which equals s squared minus 2p. Substituting s equals 2, and p equals negative 3 gives 10. Their product is x1 squared times x2 squared, which equals the square of x1 x2, that is p squared, which is 9. A monic quadratic with roots y1 and y2 is y squared minus the sum times y plus the product equals 0. Substituting the sum 10 and the product 9 gives y squared minus 10, y plus 9 equals 0. Let's verify the original factors as x minus 3 times x plus 1 equals 0. So the roots are 3 and negative 1. Squaring gives 9 and 1. Our new equation factors as y minus 9 times y minus 1 equals 0, which indeed has roots 9 and 1. Example. Our goal is to form a new quadratic equation. We start with a quadratic ax squared plus bx plus c equals 0. And we want the quadratic whose roots are 1 over ax1 plus b and 1 over ax2 plus b. Write a quadratic in the variable y whose roots are y equals 1 over ax plus b, where x runs over the roots x1 and x2 of the original quadratic. Here is the mapping from x to y. Each root x maps through the rule y equals 1 over ax plus b. Step 1. Express x in terms of y. Start with y equals 1 over ax plus b. Multiply both sides by ax plus b to get y times ax plus b equals 1. That is axy plus b, y equals 1. So axy equals 1 minus by. Finally, divide by ay to get x equals the fraction 1 minus by over ay. Step 2. Substitute this expression for x into the original quadratic. Write ax squared plus bx plus c equals 0, and replace x by the fraction 1 minus by over ay. Clear denominators by multiplying by ay squared. Then expand and collect like powers of y. Group terms by powers of y. The y squared terms combine to see a squared y squared. The y terms combine to minus aby. The constant term is a. So the new quadratic in y is c a squared y squared minus ab y plus a equals 0. Therefore, the quadratic whose roots are 1 over ax1 plus b and 1 over ax2 plus b is c a squared y squared minus by plus a equals 0. This method works for any point transformation y equals 1 over ax plus b. Solve for x in terms of y and substitute into the original polynomial. In this lesson, we will form a new quadratic equation whose roots are the cubes of the roots of a given quadratic. The given equation is x squared minus 3x plus 2 equals 0. We want the quadratic whose roots are x sub 1 cubed and x sub 2 cubed. Let's build a simple map of the transformation. We start with the two roots x sub 1 and x sub 2 on the left, and we map them through the cube function to get y sub 1 equals x sub 1 cubed and y sub 2 equals x sub 2 cubed. By Vieta's formulas for the original quadratic, the sum s equals x sub 1 plus x sub 2 equals 3, and the product p equals x sub 1 times x sub 2 equals 2. Next, we compute the sum and product of the cubed roots. The identity for the sum of cubes says x sub 1 cubed plus x sub 2 cubed equals s cubed minus 3ps. Substituting s equals 3, and p equals 2 gives 9. The product is simply p cubed, which equals 8. A quadratic with roots y sub 1, and y sub 2 has the form y squared minus the sum times y plus the product equals 0. Replacing the sum with 9 and the product with 8 gives y squared minus 9, y plus 8 equals 0. Let's verify quickly by solving the original quadratic. The roots are 1 and 2, so the cubed roots are 1 and 8. Indeed, y squared minus 9, y plus 8 factors as y minus 1 times y minus 8 equals 0. Therefore, the required quadratic equation is y squared minus 9, y plus 8 equals 0. In this example, we will form a new quadratic equation when each root is transformed by a linear rule. The original equation is x squared minus mx minus 1 equals 0, and each new root, y, is related to x by y equals 3x minus 4. Our goal is to write the quadratic in the variable y step by step. Step 1. Solve the transformation for x in terms of y. Add 4 to both sides to get y plus 4 equals 3x. Then divide by 3x equals the quantity y plus 4 over 3. Step 2. Substitute this expression for x into the original quadratic. Replace each x by the quantity y plus 4 over 3. That gives left parenthesis y plus 4 over 3 right parenthesis squared minus m times left parenthesis y plus 4 over 3 right parenthesis minus 1 equals 0. Step 3. Clear denominators by multiplying both sides by 9. We obtain the equation left parenthesis y plus 4 right parenthesis squared minus 3m times left parenthesis y plus 4 right parenthesis minus 9 equals 0. Step 4. Expand and simplify. The quantity y plus 4 squared equals y squared plus 8y plus 16. Substituting that in gives y squared plus 8, y plus 16 minus 3m, y minus 12m minus 9 equals 0. Step 5. Combine like terms to write the quadratic in standard form. We get y squared plus y times parenthesis 8 minus 3m parenthesis plus 7 minus 12m equals 0. That is the required quadratic equation in the variable y. Summary. We solve the transformation y equals 3x minus 4 for x, substituted into the original quadratic, cleared denominators, expanded, and combined like terms to obtain the new quadratic in y. In this lesson, we will form a new quadratic equation when each new root is 5 more than the negative of each original root. We will proceed step by step, keeping all algebra transparent and visual. The given equation is mx squared minus 2x plus 1 equals 0. We must build the quadratic whose roots are 5 more than the negatives of the original roots. If x is an original root, then the corresponding new root y satisfies y equals 5 plus negative x, or simply y equals 5 minus x. Solving for x gives x equals 5 minus y. This is the key substitution. Substitute x equals 5 minus y into the original equation. That is, m times 5 minus y quantity squared, minus 2 times 5 minus y, plus 1 equals 0. Now expand. 5 minus y quantity squared is 25 minus 10 y plus y squared. Distribute m, then expand the linear term and collect like terms. Arrange in descending powers of y. Group the y squared term, the y term, and the constant term. It is often written with the middle coefficient highlighted as negative 2 times quantity 5m minus 1. This is algebraically identical. Since a quadratic is usually written in the variable x, we may rename y to x to state the required quadratic succinctly. Quick check with m equals 1. The original equation becomes x squared minus 2x plus 1 equals 0 with a double root at 1. The new roots should be 5 minus 1, which is 4, also a double root. Our formula gives x squared minus 8x plus 16 equals 0, which indeed has a double root at 4. The transformation works. Final answer. The required quadratic whose roots are 5 more than the negatives of the original roots is mx squared minus 2 times quantity 5, m minus 1 times x plus 25, m minus 9 equals 0. In this lesson, we will solve for p and q given two quadratic equations. The roots of the second equation are each exactly 1 greater than the roots of the first. Let us place both equations on screen and label them. To visualize the condition, think of the roots on a number line. Each root of the second equation is the first root shifted to the right by 1 unit. Algebraically, if y equals x plus 1, then x equals y minus 1. Substitute x equals y minus 1 into the first equation. Expand and collect like terms to get a new quadratic in y. The problem states that the second equation has exactly these shifted roots. So equation 3 must be identical to equation 2. Write equation 2 in the variable y. Now, equate coefficients of y and the constant terms. From the first equation, we get p squared plus p minus 2 equals 0. Factor to obtain p equals 1 or p equals negative 2. Case 1, p equals 1. Plugging into the second relation gives 1 minus 1 plus q equals 1 times q, which is an identity. So q can be any real number. Case 2, p equals negative 2. Then 1 minus negative 2 plus q equals negative 2q. So 3 plus q equals negative 2q, which yields q equals negative 1. Therefore, the solutions are p equals 1 with any real q, or p equals negative 2 with q equals negative 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.